back to more derivatives. So, implicit differentiation. Now, there's one thing I kind of want you to think about, and the better yet, I want you to do this for me. So, I'm going to write this down, and I want you to solve for the variable y. So, solve for y, x squared plus y squared equals 4. So, get pause the video, go ahead, do that, and then after you do that, unpause it to see if you get the same thing that I did. All right, so what you should have written for a final solution is y equals plus or minus the square root of 4 minus x squared. Now, this is kind of weird. At least it should be initially, because here's a situation where we don't have, so we do not have what we call an explicit function. All right, or just an equation, really. All right. So let's understand first, what does this word explicit mean and what does the word implicit mean? Okay. Well, if you go back and you look at every single problem that we've done. So let me go back to like section 3, this differentiation formulas. Okay. If you go back and you look at every single problem we've done, notice it's always been like a function of x, or a function of x in this example, or in the quotient rule, it's a function of t. But what I'm really trying to get at here is the left hand side of the equation is some p of t or f of x or the letter y, but on the right hand side it is explicitly one variable, like t to the second plus t minus 2 all over t to the third plus 6. Even look at the chain rule. All these problems, it's y equals a function of x, okay? Or s of t equals a function of t. Or in this example here, in example E, it's f of x equals a function of x, okay? We call those types of equations or functions explicit because we can write one equation or one variable in terms of the other. A really easy example word problem that you always see is, write the function of a square, we'll put of a square's volume in terms of its sides, okay? And what this is telling you is you can write the volume of a square, v of x equals x to the third power, because remember, did I write a square here and I said volume? It's a cube. I'm sorry, it's a cube. Write the function of a cube's volume in terms of its sides. So you got to remember that a cube is not ironically, it's a square, but it's in 3 dimensions, okay? Now, a square or a cube has all the same exact sides. So if this is x, and this is x. And we know volume equals length times width times height, but since all of these are the letter x, the volume of x is going to equal x to the third power. This is an explicit function because the volume can be expressed as the product of its sides. All right? With x squared plus y squared equals 4, well, first, this is an implicit equation. And the reason for that is there is no way that you can write y equals one function of x. What is happening here is when you subtract x from both sides because you're solving for y, you're going to get y squared equals 4 minus x squared. And then to solve this for y, we take the square root of both sides. However, you got to remember that when you are solving and you apply the square root property, you get plus or minus, which means there are 2 solutions to this problem. All right? y1 equals positive square root of 4 minus x squared. and y2 equals negative square root of 4 minus x squared. Hence, this is an implicit equation. This is not a function. All right, it fails the vertical line test. In fact, let me show you two things, and this is why you got to be really careful about when you use your calculator. Okay, so let's go ahead. Let's get our calculator out. First thing you should notice, all right, is in the upper left-hand corner of your calculator, you got this y equals button. All right, so notice, in order for you to properly graph x squared plus y squared equals 4, you got to solve the equation for y. The issue is, if you did not remember, and I'm going to go back to our notes real quick. If you forgot to add that plus or minus, let's just say you wrote it as y equals the square root of 4 minus x squared, which I'm guessing at least one of us did, which is okay. We're learning this, all right? And mistakes are going to be made when you're learning. The last mistake you've made is the best teacher you've ever had, because there's an opportunity to grow from that mistake. So just remember, when you were solving, and you apply the square root property to both sides of the equation, plus or minus. So anyways, let's go back to our calculator here. Notice that if you forgot to add the plus or minus, and you just type this in, 4 minus x squared, and you hit graph, you would only get the top half of the circle. Now, here's the even bigger issue. Let's say you looked at x squared plus y squared equals 4. If you didn't notice right from the start that that is the equation of a circle with a radius 2, then unfortunately, if you were to graph this in your calculator, you would think that's the correct answer and move on to the next problem. And this is actually incorrect, because this is a circle with radius 2. So what you'd have to do is come back into the y equals. You would have to come down in the y2 and then hit your negative button, square root 4 minus x squared. And finally, when you hit graph, not only do you get the top half of the circle, you get the bottom half of the circle as well. All right? You know me. One of my favorite things is Desmos. I love it. So if I click on Desmos here, Desmos is beautiful because you don't have to explicitly solve for anything. All right? All you got to do is just type it in. X squared plus y squared equals 2. And it'll graph the circle for you, which is a great thing. All right? So as much as I love my TI-84 plus CE calculator, which I have directly to my left here, you can't see it, Desmos is the king when it comes to graphing. It's so nice. And we're going to be looking at all these different really interesting types of implicit equations, like this one right here. Sine of xy equals the sine of x plus, sine of x plus the sine of y. There is no way that you can explicitly solve this equation, yet when you graph this, it is unbelievable looking. It's one of the coolest things I think I've seen in terms of graphing functions, okay? And implicit differentiation allows us to find not only the derivative at any point, but it allows us to focus on what are the slopes of these lines and everything. I mean, this is just one really interesting example of what's happening. And if you just kept zooming out here, I mean, you can see how this actually models. And to me, this kind of looks like, when you are after it's done raining, you park in a parking lot. Unfortunately, there's like some oil on the ground, and when you look at the reflection of the oil in the water, it creates like this mosaic type model right here. So you can actually use this to model different types of natural phenomena that is happening all around us. This is just one little thing. All right. But anyways, I want to get back to this idea of implicit differentiation. Okay. Because here's the idea behind this. Let's say we wanted to find dy dx for x to the second plus y to the second equals 4. Well, the major issue with this is on the surface right now, we only know how to take derivatives of explicit equations or functions, like f of x equals something, or y equals something. So then the big question becomes, how would you differentiate an equation that's implicit? All right. And the idea, or in the goal, or not the goal, but the key to this all goes back to this chain rule. All right, it all goes back to the chain rule. So what I want to do here is I just want to show you how to do this, and then we'll talk about it. All right. So when we want to find dy dx for an implicit equation, all right, we would go ahead and what we're going to do is we're going to take the derivative like we normally would. However, when we look at the function of y, we know that y is really a function of x, which means that when we differentiate the variable y, we're going to have to apply the chain rule and multiply it by its differential. So here's what I mean by this, all right? First thing I'm going to do, let's go ahead, let's take the derivative going from left to right, okay? So the derivative of x squared is going to be 2x plus. Now, here's where implicit differentiation is going to kick in. We can go ahead and take the derivative of y to the second, and that's going to be 2y. However, this y to the second is really y of x to the second, which means you're going to take the derivative using the chain rule of 2. So you pull it out front, subtract it from 1, and then you're going to multiply it by the derivative of the inside function, which is y prime of x. Now, we don't really, I mean, if you wanted to, you can write y prime of x, but personally, this is the only time where I'm being very specific. What I like to do is multiply it by dy dx. And the reason why I choose to use dy dx and not y prime of x is because it is easier for me to see. That's it. That is it. It's easier for me to see. Now, on the far right-hand side, the derivative of a constant is 0. Now, we know the derivative notation is dy dx. So all we have to do now is just solve this equation for dy dx. So if I just subtract 2x from both sides, I get 2y dy dx equals negative 2x. And then divide both sides by 2y, because remember, we are solving for dy dx. So we get dy dx, which is our derivative, is equal to negative x minus y. All right, now let's take this one step further. Let's look at another very similar problem, okay, because I want you to see this again. We want to find the equation of the tangent line to, like I said, it's going to be a very similar problem. So we're going to look at another circle. This time we're going to look at it with a radius of 3 at x equals 2. Okay? Now, like I said, one thing we do got to be worried about, what quadrant are we talking about? So I'm going to limit this to quadrant 1, and you'll see why in a second. So let's go ahead. Anytime you see the words, find the equation of the tangent line, you got to remember. All right, and it doesn't matter the order in which you do this. I'm just going to write them down. First thing you need is a point. Second thing is you need the derivative. Oops. Dy dx evaluated at x equals a, wherever that value is. And then 3, we're going to use y minus y1 equals dy dx evaluated at a times x minus x1. So our point slope equation with our derivative, which is now the slope of the tangent line. So first, let's get our point. I'm just going to do it off to the right-hand side here. I think it's easy enough. So x is going to be 2. All right. So I get 4 plus y squared equals 9. Subtract 4 from both sides. We get y squared equals 5. Taking this square root property of both sides. Don't forget to add your plus or minus. Y equals plus or minus the square root of 5. Now, hopefully you can see why I'm restricting us to quadrant 1, because our point is going to be 2 comma square root of 5. The other point, 2 comma negative square root of 5, is in quadrant 4. Okay? So I am restricting us to quadrant 1. Second, got our point. Now we need our derivative evaluated at x equals a. In this case, the a is 2. So I'm going to scroll down. X squared plus y squared equals 9. Now our derivative, we're going to have to use implicit differentiation because we cannot solve this equation for y explicitly. So going from left to right, we get the derivative of 2x plus 2y dy dx. Remember, that y squared is really y of x raised to the second power. So you're taking the power, you're pulling it out front, and then you're multiplying it by the derivative of the function itself, which in this case is going to be y prime, all right, using the chain rule. And this is going to equal 0. So now solving for dy dx, we basically get the same exact thing as before. We get dy dx equals negative x over y, all right? Except now we have to evaluate this at x equals 2, y equals the square root of 5. So let me go back up here. I need to be a little bit more specific now. Y equals the square root of 5. So dy dx is going to equal negative 2 over the square root of 5. And we'll leave it like that for now. All right. We're not going to rationalize the denominator or anything like that. All right. So here's my derivative. And now finally, step 3 is just y minus y1 equals our derivative times x minus x1. So y minus the square root of 5 equals negative 2 over the square root of 5 times a quantity x minus 2. And if you wanted to, you can solve this for y, okay? So I'm not going to go too crazy with this. Y minus the square root of 5 equals negative 2 over the square root of 5x plus 4 over the square root of 5. And I'm just going to write it like this. I'm not going to get crazy with this. It's no need. I'm just going to add the square root of 5 over to the other side of the equation, just so we get a nice line that looks like this, okay? If you wanted to, you can find a common denominator and group them together. I am not going to do that at all right? But what I am going to do is this. I'm going to label everything in Desmos for us, because it's good to see this. So first, let's get rid of you. Here we go. So the first thing is we got the circle, x squared plus y squared equals 9. So there's our circle. Here's our point, 2, comma, the square root of 5. All right, let me zoom in here. There we go. So you can see that not only do we have the circle, but yes, the point is definitely on that circle. I'm going to change the color. I'm going to make it black. There we go. And then finally, we're going to go ahead and just type in our equation of the tangent line that we found. Y equals negative 2 over the square root of 5. What was that? X. Sorry, I forgot it already, so I got to go back and look at it. Plus 4 over the square root of 5. Plus 4 over the square root of 5. And then I think it was, it was plus the square root of 5. Plus the square root of 5. And as you can see, on that nice purple line that I'm definitely going to change to red and make it dotted. Here we go. There's our circle with the tangent line exactly at the point 2 comma the square root of 5, which is perfect. That's what we wanted. That's all we wanted. So now the big question is, okay, well, we're so used to seeing functions and everything. Like, why is this happening? Okay. And the reason is just because we don't have a function. Remember, this circle is not a function. It fails the vertical line test. All right. there are these other types of equations that exist. Now, some of us, you may have seen it in pre-calculus, and some of us you didn't. And it's a shame if you didn't, because they are really interesting questions. All right. Or really interesting types of equations and what they're called. And I'm not going to go too far into this, okay? Because you will learn about all this in Calc 3. But we have these types of equations called parametric equations. And parametric equations allow us to study functions. No, I don't want to say that. Parametric equations allow us to study different types of scenarios or situations where you don't have a function. So what you do is you say, well, you say y is really a function of t. So y equals y of t. And x is really a function of x of t. X of t. So we say x equals x of t, y equals y of t. And what this tells us is we can find the position of any type of, and I'm gonna be very vague, any type of situation with x and y being functions of t. Meaning, at any time t, we want to know what is the x and y position of this particle, for example. Okay? So I'm going to go ahead and do like I'm going to show just like another example of this. And what I want you to do is think about, okay, well, number one, what does this look like? And then number two, how does this look in terms of, x and t? Or I'm sorry, not x and t, x of t and y of t. So the example that I want to look at here is this. I'm going to graph it for us first. All right, so this is going to be x to the third plus y to the third equals 6xy. Okay, and this actually has a special name. All right, this is called the Folium of Descartes, and it's just the equation right here. All right. Now, here's the thing. We know that from 0 to basically a little bit after 3, okay? Not a function. Like if you restrict your domain to either x is negative or x is greater than what is this? What is this far side all the way over here? You gonna let me click on it? No, it's not even gonna let me click on it. That's fine. So where my cursor is right here, I'm gonna bring this straight down. So like I said, it's a little bit more than 3. Anyways, if you restrict your domain, you may have a function, but in this case, we don't have a function. However, I could tell you exactly where this particle, if a particle is following this trajectory, all right, x cubed plus y cubed equals 6xy, all right. So if this particle is following this trajectory, I can tell you exactly where it is at any time t. So for example, this is going to be kind of hard for me to do, so I'm going to zoom in and hopefully you could see my mouse, my cursor, okay? Right now it's at like it's at the value 1. All right? So sorry, I don't know how to change the colors of this stuff. But at t equals 1, the particle is going to be right here on this curve. At t equals 2 seconds, it's going to be right here. At t equals 3 seconds, it's going to be like all the way up here, all right? But then it starts looping around, all right? Now, as you can see here, you got 1 and 2, but you got to understand the 1 and 2 correspond to x values. T just means time. So as time progresses, our particle is going to follow this curved trajectory right here. Okay, the x-axis and the y-axis just tells me the position. All right, but if we think of x as x of t and y as y of t, then we can differentiate this with respect to t. Okay, and that's really what this is all about. So let's go ahead and let's look at find dy dx for x to the third plus y to the third equals 6xy. So that's going to be our first thing. Our second thing that we want to do is find the tangent to the Folium of Descartes. Oh, forgot the S. Cartes. There we go. At the point 3, 3. And then the final one would be at what point, and this is going to be an introduction, this part C, to what we're going to be doing in chapter 3. So at what point in the first quadrant is the tangent line horizontal? All right, and that is a huge, huge concept right there. So I'm going to put like a little star next to C because we're going to be doing a lot of that in chapter 3. All right, so first things first, we got to find the derivative by using implicit differentiation. You got to be careful with this. So part A, x to the third plus y to the third equals 6xy. Now going from left to right, when I differentiate, I'm going to get 3x to the second plus 3y to the second times dy dx. Remember, y is a function of x here, and you got to use that chain rule, okay? So you get 3y to the second times dy dx. It's the right-hand side that we really, really, really got to be careful with, and that's because on the right-hand side, you're going to have to use the product rule because you have two different functions there. And remember, when you have two different functions, you got to use the product rule when you're multiplying. When you're adding or subtracting, it is just straight up derivatives. But if you're multiplying 6 times x times y, that is a product rule. So what I'm going to do over here, all right, is I'm just going to go ahead and write f equals, and I'll just make it 6x, which is fine. The derivative of 6x is 6. G equals y, so the derivative is going to be 1 times dy dx, or just dy dx, okay? So given our product rule, we're going to get 6x dy dx plus 6y, okay? So if you need to, rewind a video, go back, check that out. Now here's the key. We know we're solving for dy dx. So what I'm going to do for us right now, I'm going to copy and paste what we have above. Here we go. Oh, why'd you put it all the way over there? It's no fun. There we go. And I'm going to get out my highlighter because I'm going to show you something. And it's really not hard at all. I'm going to highlight all the terms that have a dy dx in common. So that's going to be this term right here. And then on the opposite side, it's going to be this term right here. Okay? Now, if our goal is to solve for dy dx, I'm going to get those two terms on one side of the equation, and then everything else on the opposite side of the equation. So, going from left to right, I'm going to have 3y squared dy dx minus 6x dy dx equals 6y minus 3x squared. So all I did is if it's, that 6xy, or I'm sorry, 6x dy dx was positive on the right-hand side of the equation. If I move it to the left, it's now negative. And then the 3x squared was positive on the left. So I move it to the right-hand side. That's now negative. Now from here, notice that both terms have this dy dx in common. So I will factor it out. That's going to give me dy dx times a quantity, 3y squared minus 6x, equals 6y minus 3x squared. Finally, I will divide both sides. by 3y squared minus 6x. And that's going to, oh, sorry, I copied down the wrong thing. 3y squared minus 6x, and that's going to give me dy dx equals, and I'm going to put the variables on top of each other so it looks the same. And I'll put the x's first. Negative 3x squared plus 6y over negative 6x plus 3y squared. And there's a little bit more simplifications you can do here, but I'm not going to worry about that. So here's our dy dx. So part A is now done. Part B, all right, is they want that find the tangent to the folium of Descartes at the point 3, 3. So we need this point 3, 3. And we also know anytime you find the equation of the tangent line or just the tangent itself, we need this right here. So the first thing I'm going to do is find dy dx numerically. So dy dx is going to equal. Now I like to go ahead and put my parentheses first. Then I'll make my substitutions. Luckily for me, it's 3, 3, so I don't have to worry about anything. Just go ahead and make my substitutions. All right, and then I'm just going to go ahead, pause the video, use my calculator. All right, I'm back, and I came up with -1 as my dy dx. So dy dx equals -1. So here's my tangent. Now the equation of the tangent line is just going to be y minus 3 equals -1 times the quantity x minus 3, which is y minus 3 equals -x plus 3. Or if you want to, you can solve by adding 3 to both sides to give us y equals -x, plus 6. All right, so let's just check, make sure we're correct. So we go back to Desmos real quick. We label the point 3, 3. Notice there's the typo. That's why I always check WebAssign for typos. All right, let's go ahead. Let's label that. And then finally, y equals -x plus 6. And there is our tangent line at the point 3, 3. And that is perfect. We'll change it to red and we'll make it a dotted line. So now the question becomes part C. Let's go back. Part C is, at what point in the first quadrant is the tangent, horizontal, okay? Now, if you go ahead and you look at the curve. So here's our curve right here, okay? I'm going to turn off our equation of the tangent line real quick. All right, so it looks like right about here where my cursor is, okay? So I'm going to move my cursor up and down real quick. It looks like right about in this area right here is where you're going to have a horizontal tangent line, all right? So we got to try to find what that point is. So let's go back to our notes. All right, and let's think about this. So, excuse me. The tangent line, or let's write down what we know, all right? We know that the tangent line will be horizontal when it equals 0. In other words, an easier way to say that would be when dy dx equals 0, okay? So we can use our dy dx from the very start. So remember, dy dx equaled, you know what I'm going to do? I'm just going to copy and paste it. It's just easier. So from part A, here's our dy dx. So let me copy this. All right, I'm just going to paste it. Here we go. All right, and what we want to do is we want to set this equal to 0. Okay? But here's the big issue. If you look on the right-hand side, we got x's and we got y's all over the place. All right? But here's what we know. I'm going to write down this statement first and then we'll explain it. We see that dy dx equals 0 when, and give me a second here. Negative 3x squared plus 6y equals 0. Okay, so I wrote this down. Now let me explain what's happening here. All right. First, on the left-hand side, that's our derivative, and we're setting it equal to 0. Now, if I wanted to, let's say, solve this equation right here for the variable y. Okay, so if I wanted to solve for y, notice that you got y's in the numerator, but you also got y squared in the denominator. Okay, but here's what's happening. If I'm solving for y, I can multiply both sides. All right, I can multiply both sides of this equation. Just give me a second. I'm just writing it out real fast. If I multiply both sides of my equation by my denominator, notice that the denominators on the right-hand side reduce. 0 times negative 6x, plus, or the quantity negative 6x plus 3y squared equals 0. Now, I can still solve for y. I'm going to go ahead. I'm going to add 3x squared to both sides. Divide both sides by 6 to give me y equals 1/2 x squared. Okay? So I know when y equals 1/2 x squared, I get 0. So I'm going to use that to my advantage. I'm going to take what I have here, and I'm going to substitute it back into the original equation because I need to know what is that x value? When is that position? Okay? Now, before I move any further, I just want to go back over this real quick. All right? Part C is asking us, at what point in the first quadrant is the tangent horizontal? The only way a tangent line is horizontal is when you have the derivative equal to 0. So, instead of me writing dy dx, I'm going to write 0. So that's what I did right here. Okay? Now, I can choose to solve for either value here, x or y. It doesn't matter. I chose to solve for the value of y. And the reason for that is if you look in the numerator at x squared, notice that eventually you would have to take the square root property of both sides because you have x squared, and that's going to introduce a plus or a minus. And I don't want to deal with plus or minuses. So I'm going to solve this for y. Now, by solving it for y, I also see that when my derivative is set equal to 0, so that's on the right-hand side, that's right here, I'm circling it for you on your screen. When the derivative will equal 0 when negative 3x squared plus 6y equals 0. In other words, my derivative equals 0 when my numerator equals 0. Okay? So I just went ahead and I solved and I said, okay, well, when will that numerator equal 0? And that numerator will equal 0 when y equals 1/2 x squared. So I'm going to take that and I'm going to substitute it into my original equation, and that will give me the position or the x value when that occurs. So I just go ahead and I make the substitution appropriately. And then I'm just going to go ahead and solve. So on the left-hand side, you get x to the third plus 1/8 x to the sixth equals 3x to the third. excuse me. Now I will solve for x, and this is going to be a doozy here. So the first thing I'm going to do is just multiply everything by 8. That gives me 8x to the third plus x to the sixth equals 24x to the third. Now I will subtract 8x to the third from both sides of my equation to give me x to the sixth equals 24 minus 8 is 16x to the third. All right, from here, there's multiple ways you can go about this. What I'm going to do is I'm just going to write it like this. All right, x to the sixth minus 16x to the third equals 0. Factor out my x to the third. X to the third equals 0. X to the third minus 16 equals 0. So x equals 0 here, all right? But we're not going to worry about that because looking at our graph, we know that is just the x-intercept. What we're concerned with is where is this tangent line actually going to happen? And we know it's going to be to the right of 0. So this is just going to be x to the third equals 16. And then you will take the cube root, all right, of both sides. All right. Now, by taking the cube root, you're still going to get that plus or minus, but I'm just going to leave it plus because we're in quadrant 1. And then to go ahead and reduce this, you're going to get, oh, sorry, I forgot to write x to the third there. So to reduce the right-hand side here, let's rewrite this as 16 to the 1/3 power, which is x equals 2 to the 4/3 power. Now, if I went too fast for you there, remember, 16, all right, is really 2 to the 4th to the 1/3. And when you have an exponent raised to an exponent, you multiply the exponents together. But at the end of the day, x equals 2 to the 4/3 power, right? And if you were to type that into your calculator, you'd get something like x is approximately 2.5198. And then this is the x value of where that horizontal tangent line happens. So then, now that you know x, you can easily just solve for y by substituting it back into the original equation. But the point that you're going to get is approximately 2.5198, comma 3.1748, which is reasonable. And I'm going to use this word. It's reasonable enough. All right. Can't spell. Reasonable enough. I mean, ideally, you want to use an exact answer. So you would use 2 to the 4/3 power, but then you'd have to take 2 to the 4/3 power. All right. And you'd have to substitute it back into this equation and then solve for y. So you're going to end up getting another decimal anyways. But if we go back and we just kind of plot these this point right here. So just give me 1 second. Let me go back to Desmos. Turn off this point. Actually, no, I'll leave it on. That's fine. And I'm just going to go ahead and give our reasonable enough answer. So we got 2.5198, comma 3.1748. Now, it's not perfect, obviously. However, you can see that it's really, really close to where we thought that horizontal tangent line would be, which is right here. All right. And that's going to be it for this video. All right. Actually, you know what? No, it's not going to be it for this video. I just want to go back and review everything that we've done so far because we didn't do too many examples. It's just you got to know how to do it. So first, let's go all the way back up. We're just going to review real quick. Implicit differentiation allows us to take the derivative of what we call an implicit equation. It's an equation that cannot be explicitly solved for one variable. All right. To do that, you need your chain rule. All right. So the independent variable, which is x, you would just go ahead and take the derivative, but that dependent variable y, because remember, we're looking for dy dx. All right. This y to the second power is really y of x to the second power. So you need to go ahead and implicitly differentiate that, which means, or I'm sorry, using the chain rule. So pull the power out front, and then you multiply by the derivative of the inside, which will just be dy dx. All right, so you do that anytime you see a variable y. Then you go ahead and you solve for dy dx. Now, sometimes it's really easy to solve for dy dx, but in the second example, let me scroll down. And the second example was a little bit more difficult because what you had to do is you had to use this chain, or I'm sorry, you had to use the chain rule along with the product rule. Okay, so you got to be careful when you have something like 6 times xy. All right, you got to use the product rule or whatever differentiation rule that we need to apply. That's what you put there. Then you're going to go ahead and the key after you implicitly differentiate is to solve for dy dx. Once you do that, you're going to have your derivative. If they give you a point, you can find equation of a tangent line. You can find horizontal tangent lines if you wanted to. I'm going to make sure that like on a quiz or exam, they're going to work out very nicely. Like this problem right here was not a very nice problem, only because we got a reasonable enough point to find our horizontal tangent line. I'll make sure that it works out nicely. Okay. So good luck, and I'll see you in the next video where we're going to be talking about related rates, which are nothing but application problems. So see you later.